Welcome back. This time we're going to do some more examples about integrating over non-rectangular regions. Here is a double integral of a relatively simple function. Because the function is relatively simple, then we are going to focus on which is the right way to slice. So we have two functions here, y is equal to x minus 1 and y squared equals 2x plus 6. When we're doing a double integral, we always want to draw a picture that talks about so that we can see what it looks like. So y is equal to x minus 1. That's this function. Y equals x minus 1. And then we look at the function y squared equals 2x plus 6. So if we subtract 6 from both sides, y squared minus 6 is equal to 2x, or x is equal to 1/2 y squared minus 3. So that's a parabola opening upward in the direction of y, but shifted back 3 units. So that looks like this. This is our y squared equals 2x plus 6. All right, so we look at this region and we have to do that same type of investigation. Which way should we do our slices? Well, let's consider our vertical slices again. So if we were to do some vertical slices, would we run into the same function on both ends of our vertical slices? Well, if we look at this red line here, if we're on the right side of this red line, then the upper function is the blue curve, and the lower function is the black line. Right? So if we look at all of these vertical slices, you're in this setup where you can slice your region and everything has an upper function, that's the blue curve, the lower function is the black line. But if you're on the left side of this red line, you actually have a different set of upper and lower functions. You have the same upper function, which is that blue curve, but the lower function is again the lower half of this parabola. And so what that's telling me is that vertical slices are probably not the way to go, because the region doesn't have the same upper function and lower function the whole way through. That doesn't mean it's impossible to do this integral in terms of vertical slices. Right? If we wanted to do this integral in terms of vertical slices, we could do two different integrals. We could do the integral on the left side and the integral on the right side. We could set up an integral where we have the upper half of the parabola and the lower half of the parabola as our bounds on of the y. And on the right half, we could just do two different integrals. We could add up those regions. Right? If you have some really complex region, you may have to break it up into two pieces, where you do one integral over this region and one integral over this region. It's not possible at all to draw this, draw vertical slices in this region, and even the horizontal slices also look like they could be complex, right? I could even draw a picture that looks like this, and you could imagine that your function, you're going to have to deconstruct this region into multiple pieces. So that's an aside. What we're saying is that no matter what the region looks like, no matter what this D domain looks like, we could chop it up into pieces and we could always do vertical or always do horizontal. But in this situation, our life is going to be so much easier if instead of slicing vertically, we slice horizontally. So what does a horizontal slice look like? A horizontal slice looks like this, in which case you have a lower function or a left function, and you have an uppermost function or a right function. And so what this is saying, this is that we called this a type 2 region. But in any case, we know that if we're doing these horizontal slices, we're going to need to know where do we start chopping and where do we stop chopping, and what's the upper function, what's the lower function. So we look at this and we say, okay, so the places where we start and stop chopping correspond to the places where you have an intersection. So what we need to know, right, here's what we're doing. This is y is equal to c, and this is y is equal to d. We want to know what are the y coordinates where these two curves intersect. So in this case, what do we have? We have if y is equal to x minus 1, we want to solve for y, so let's say x is equal to y plus 1. We'll plug this in here. So we have y squared is equal to 2y plus 2 plus 6. So y squared minus 2y minus 8 is equal to 0. So y minus 4 times y plus 2 is equal to 0. So y is equal to 4 or negative 2. So that's saying that this point right here is at y is equal to negative 2. And I guess that means that x is equal to 1, or negative 1, sorry. And this point right here corresponds to y equals 4. And so x is equal to 5. But we care mostly about this y equals negative 2, y equals 4. And we need to then think about what the upper function is and the lower function. So as we set up this integral, we're going to look at y is equal to negative 2 to y is equal to 4. That's where we start chopping, and that's where we stop chopping. And now we have to set up our integral, where we have our lower function and our upper function. So the lower function is on the left side, the lower y values. And we see that that is this function, x is equal to 1/2 y squared minus 3. And this function we also have to write in terms of x. X is equal to y plus 1. What I really wanted to do is I wanted to put that in red, because that's what we've been saying for our upper functions. X is equal to y plus 1. And then we're going to integrate whatever our integral was, xy dA. And because we're doing our integral, so integrate xy, we're integrating first with respect to x and then with respect to y. So here we've now set up our integral. This outer integral has to do with where we're chopping, and this inner integral has to do with what the bounds of the slices are. I think that's the key part of this example is coming up and doing the setting up the integral.